Chapter 2, One-Dimensional Motion. Now, motion could either be translation, in which the object goes from one place to another, which may be in a straight line or not. And then we have the second kind of motion is rotation, in which the object may just be spinning, like the Earth is spinning. So the center of mass stays where it is, but it just keeps rotating, or like a top. And the third is vibration, in which it's like a pendulum, where the pendulum swings back and forth. So it's moving, but it comes back to the same place repeatedly. So we will cover all of these in different chapters. So what we're doing now is what we call translation. And we will deal with translation in one dimension, meaning that the object can only go forward or it can go backwards. So it's only going to stray in a straight line. It can go far or close, but it will not bend up or down. So with this, we now need a few definitions. And the first is, we like to define position. And we write position as an x, and the unit is a meter. So if we take a straight line and we say this is our initial position, we take it as x equal to 0, then if the object is here, it has some value of x. So we'll say its position, if the object is here, we'll say its position is at some value of x, which is some number. X could be positive, or it could be a negative number. It could be x1, that could be minus x2. So position is a vector, and it could be positive or it could be negative. Now the second thing we want to is distance. And let's suppose we'll make another one here. So this is x equal to 0. Let's say 2, 4, 6, 8, 10, and well, can keep on going. Let's suppose the object was initially here at x equals 4. So that's the initial position A. And then it moves on to position B. So it goes from A to B. And so the distance it has traveled is going to be from here to here, which is 6 units. So it's 6, and let's suppose these are all meters. So the distance is 6 meters. Now, if it were going from B to A, it would still be 6 meters, because distance is always positive. Now let's suppose that the object went from A to B, and then it turned around. Well, it didn't turn around, but it went in reverse, because to turn around means it's in 2D. So it goes straight and then goes back in reverse up to the point C. So now the distance, this was the distance between A to B, the distance between A to C is going to be 6 units this way and 4 units this way. So it's going to be 6 plus 4. So it's 10 meters. So whether you're going forward or backwards, the distance will always add up. So distance is always a positive number, and it's a scalar. Now with this, we define what we call the average speed. The average speed is the distance traveled over the time taken to travel that distance. So let's suppose that when the object was at A, the t was 0, and at B, t is, let's say, 2 seconds. and by the time it reaches C, here the T, let's say, is 4 seconds. So you have a stopwatch, start it off at A. When you reach B, you notice 2 seconds. When it comes back towards C, you note it's at 4 seconds. So now the average speed between A and B is the distance from A to B, which is 6 meters over 2 seconds, so that's 3 meters per second. And the average speed between A to C is going to be 6 plus 4, 10 meters, like we had here, divided by 4 seconds. So it's going to be 2.5 meters per second. Now this does not tell us anything about the speed that it had at this point or any other point. It just gives us the average between A and C, or between A and B. We will now define what we call the displacement. So displacement and distance are different things. It's a vector, whereas distance is a scalar, and it could be positive or it could be negative. So if the displacement is towards the right, we take it as positive. If it's towards the left, we take it as negative. Now we look at the same 3 points, A, B, and C. So the displacement is written as a delta x, and the delta x, the displacement from A to B, would be x at B minus x at A. So that's going to be 10 minus 4, which is going to be 6 meters, which is the same as the distance in this case. Now the displacement between B to C, that is this backward path, is going to be x at C minus x at B, which is going to be 6 minus 10, sorry. That's going to be minus 4 meters. So the distance was 6 from here to here and 4 here to here. They added to 10. But the displacement is 6 and negative 4. And therefore the displacement from A to C is going to be x at C minus x at A. It's always the final minus initial. The final position is 4, the final position is 6, and the initial position is 4, so it's plus 2. So the displacement between A to C is plus 2, whereas the distance from A to C was 10. The displacement is a vector, and it just tells us that if it was here in the beginning and now it's here, how far is it? So if an object started from here, it covers the distance like this, the distance would be all of this entire path, but the displacement would just be from here to here. This would be the delta. Well, it's not 2D, but this would be the displacement. Only the final position minus the initial position, whereas the distance would be the entire path that it takes. Now, just as we have an average speed, we would have an average velocity. And this we would write as a v. The units would be meters per second, and it's defined as v average equals the displacement over the time. So not the distance, but the displacement over time. And therefore the v average from A to C would be the displacement from A to C, which is 2 meters, and the time is 4 seconds. That's what we had here. The displacement is 2 meters and the time is 4 seconds, and that would be 0.5 meters per second. So the average speed was 2.5 meters per second. The average velocity is only 0.5 meters per second. Well, ultimately, if this object had come back all the way to the same position, if it came back to A, the average speed would have some value, but the average velocity would become 0 because the displacement would become 0. So you may go from one point to some distance and come back to the same point, the displacement becomes 0. And if it had gone from A to B and then gone here, the displacement would have been a negative number. The distance would always have been positive. Now, the average speeds do not give us any information about what would have happened as it was going along. So what would be the speed at any individual point? It is not given by the average values. For that, we need the instantaneous values. So we have the instantaneous speed and the instantaneous velocity. Now, these are written, the instantaneous velocity is written simply as a v, and the instantaneous speed will also be written as a v. Now, this is, if you're going from this position to here, so that's x final, that's x initial, and so this is delta x, and the time taken to go from here to here is delta t. So the average velocity is delta x over delta t. Now, if we want the velocity at this position right here, the instantaneous velocity, what is the velocity when the point is crossing that point? Well, we can take 2 points here and here. This would be our initial position and the final position, and we note this is the delta x, and we note a small delta t, and then we can say the delta x over delta t. That would still be the average velocity over this path. So to get the velocity right at that instant, we would have to move this initial and final positions close to each other until they just merge together. And that we do in calculus. So we say that the instantaneous velocity is the limit when delta t tends to 0, which means these 2 points approach each other, and this becomes the instantaneous velocity, and we know that that is dx over dt. So this becomes the slope of the curve. If we draw a curve with t and x, so at x initial, this was whatever the value, it doesn't have to be 0, so that's x initial, and this is x final at some t, so this is delta t. So if we draw a curve, then the slope of this line, well, it could be a curve, so make it a curve. It's like that. Then the slope of the line at that point, dx over dt at that point, is the instantaneous velocity at that point, and the slope at that point would be the velocity at that point. So this is what we call the instantaneous velocity.